Right, so I'm sorry that Mihaly can't be here, so please bear with me. Don't blame me if I mess it up, but I probably know enough about this stuff to give you the story. Okay, so this talk is about the dust environment of airless planetary bodies, and so the talk consists of two parts. So we will report about the new evidence we acquired with space probes about the lunar dust cloud, and we will also report about processes on the surface of airless bodies which are powerful enough to actually activate the dust which can be found on the surfaces of such bodies and to cause lateral motion and a restructuring of the surface. Okay, so the first part is about the dust environments, dust clouds around moons, which are basically produced by micrometeoroids impacting the surface and by doing this, generating ejecta which populate these clouds. And there are actually two sources of such micrometeoroids which can produce ejecta: meteor showers and sporadic meteoroids. So basically, when we started to put together the instrument for NASA's LEDI mission, which was supposed to explore the exocloud, the dust exocloud around the moon, what we assumed is the scenario which has been found by the Galileo dust detector in the Jovian system. The Jovian dust detector found dust clouds around all of the Galilean moons. And this is an example for my beloved moon Europa. Yeah, it's a collection of data from of roughly 10 flybys, and the number densities as function of the altitude, they follow quite nicely this kind of power law, which is basically the density which you obtain when you assume that the particles which are lifted off from the surface move on Keplerian orbits around the moon, and they fall back, they recollide, as a result of that, there's a steady state dust cloud. And the important point is those clouds are isotropic. And this is exactly what we expected for the moon, and we couldn't have been more wrong. And then after we had a deeper look in our data, we actually realized that it was pretty stupid from us, because it's pretty obvious why is it not so. Yeah? Okay, let me tell you. So this is the little LEDI spacecraft, and it carried a dust detector, which is actually this tiny thing here. And the orbit was designed in support of UV observations of the terminator, and that's why they picked an orbit which is not really the best choice for exploring a dust cloud. Yeah? However, we had many flybys, and this allowed us to collect the particles. So this is a schematic view of the LDEX detector. It works pretty simple. A particle entering the instrument hits the hemispherical target made of gold. The impact energy is sufficient to ionize the particle, at least to some extent. You separate the charge in an electrostatic field between a spherical grid in front of a multiplier. You collect the positive charges on the multiplier, the negative charges on the impact target, and the amount of the plasma tells you about the mass of the particle. And this allows you to characterize the environment. The instrument has been calibrated at the University of Colorado at the Dust Accelerator, which allows you to shoot particles of known speed and mass into such an instrument. This gives you, this allows you to record the response of the instrument to such an impact, and the amplitude of the signal, again, is a measure for the mass, and actually the time it takes the signal to rise to its maximum value is a measure for the speed. Okay, so this is a snapshot, or it's actually the overall average impact rate normalized to a certain altitude during the mission. The mission was pretty short, and what you actually see here is we have a kind of a flat impact rate, which is the result of moving within a dust exosphere. And at the same time, we have these spikes here. This is the unexpected part. This is actually meteoroid showers showing up in the density of the lunar dust cloud itself, which is kind of nifty. So then the first thing we actually tried to do is to reproduce the Galileo findings. So we had this beautiful model for an isotropic cloud, and if you single out the right local time, which is shown here, you will see this kind of figure multiple times. If you just single out, a certain fixed value of local time, and you plot the density of the particles, number density as function of the altitude, we again reproduce beautifully the dust cloud model for airless bodies. And there is a dependence on local time. This is shown here. This is local time, and the density is scaling with the local time. The density actually at the night side is lower. At the terminator is the highest. Okay, so nifty. The next thing Mihaly and his grad student did was to model actually the impact of flux from the known populations in the interplanetary space, what they call sporadic meteors. There are 3 families. And this leads to a pronounced asymmetry. But you still may ask the question, so why haven't we observed this asymmetry in the Jovian system? And the answer is pretty simple. That's why I found it actually a little bit embarrassing after we realized what's really driving this. The Jovian system, the data have been acquired very, very deep within the Hill sphere of Saturn, of Jupiter. And as a consequence of that, particles, so the primary impactors entering the system on hyperbolic orbits get sufficiently randomized once you are so close to the planet, and so the impact of flux is isotropic, and so you end up with an isotropic cloud, more or less. And the colleagues working on the Galileo data actually investigated that. They really tried to identify the asymmetry and the impact of flux, and it was almost impossible to even see the imprint of that. The Earth-Moon system is completely different. In terms of gravity, Earth and Moon are not big players. The Hill sphere is not sufficient to sufficiently randomize the impact of flux, and so we clearly see the directionality of the primary impactors in the density of the cloud, which is shown here. You end up with a cloud which is strongly asymmetric, which is pointing toward the average impact of flux direction. And there's more in the data, because once you start to model this in detail, you end up with variations which really showed up in our data. There is a slight annual variation, which is due to the proper motion of the moon around the sun, around the Earth. And there's also an annual variation, which is because of the proper motion of the Earth around the sun. Both shows up in our data. Okay. The meteor showers, they actually showed up prominently in our data. And this is really a powerful tool, as it turned out, to identify such meteor streams. So we even saw streams which are not observed from Earth. And the reason why you can do this so efficiently with a small detector around the moon is that basically the whole moon acts as an flux amplifier of these meteors, because every single meteor hitting the surface is generating millions of ejecta, and they show up in our data. Jamie compiled a list of meteor streams which have been expected during the time of the mission to impact the moon, and here he lists basically if we have seen the meteor streams in our data or not, and we basically have detected all of them. Okay, let me just jump through it because we are short on time. Something you can do with such an instrument, you can actually do a time-resolved measurement of the structure of the meteor stream. Mihaly and Jamie are working on this to improve this and to have this, reflected in simulations of the meteor stream structure itself. Okay, so the second part of the talk is about near-surface dust plasma effects. That's the other cup of tea we are dealing with. So in our lab, we have setups to actually, which allow us to model the motion and the actuation of dust analogs under realistic condition. This is Riga gamma, and so this kind of research has been driven in part to reproduce the observed albedo features in this region. Okay, so what we actually do, it's a pretty simple setup. It's a plasma chamber which allows us to expose a dust sample either to UV or to a weak plasma, ionizing plasma, and we have a camera system which allows us to observe the motion of the dust. And the irony here is that we tried to do this for years. Yeah? We tried to do for years to observe any effect of plasma or of UV on dust, and we never really observed anything. Yeah? Until the Japanese TV wanted to take a movie from our lab, yeah? And they showed up with these big-ass cameras, yeah? Ultra high resolution and high speed, and they just wanted to see some dust. And so they convinced us to allow them to actually use a camera on our chamber. And because the illumination conditions were not sufficient, they used bigger lamps. And when they did this, they observed something really crazy. Yeah? You can actually see this here. You see this? Yeah? So what we realized once we used stroboscopic light was the hopping motion of the particles. They really started to hop. Yeah? And the weird thing is, if you pull together your freshman physics and you just do the math, yeah, is it possible? Where are the forces coming from? Yeah? It doesn't work. Yeah? This, to some extent, at this point, violated the rules of nature. Yeah? This gave us a hard time, actually, Mihaly's postdoc Shu Wang to convince the editors of journals to even accept it for print, yeah? Because the physics was somehow shaky, but it was obviously doing its job. And so because Shu is a careful experimental physicist, so he explored the parameter space. He verified it's not just working with UV, it works. The only thing you have to do is you have to charge the surface, and you have to charge the surface in a very specific way. And what they have figured out is that the mechanism which is really driving the process is that you have to have cavities in the surface. Yeah? And the isophotons, or energetic ions, entering these cavities produce secondaries. The secondaries lead to a local change of the potential within these cavities, and then under those conditions, the electric field is strong enough to actually activate the particles. And so let me show you how it works. So this is just a sample of Mars analog exposed to UV. Yeah? It's about, they didn't tell you what is the energy of the UV. It's a few electron volts. And you basically see this ant-like motion of the stuff. And after playing long enough with this, we managed to move the stuff from inside the cavity to the surroundings. We could push the stuff from left to right. Yeah? So we can basically model ponding, yeah, observed on asteroids with this process. However, in order to make sense of Riga gamma, this is, I think, the cooler stuff. So here, the additional element in this experiment is to use a magnetic dipole parallel to the surface. And so we covered the sample with white stuff to really see what's happening. And this is actually causing, a kind of an organized transport across the surface. So it really allows you to establish albedo patterns once you have defined local magnetic fields at the surface. And you also see that, you know, we push stuff to the exterior of this little pit with dust. Okay. Yes, and so the last slide is the open questions compiled by Mihaly. And I probably leave you with that. Thank you.